Let's talk about random variable. Because of random variable, we are able to numeralize the results of an experiment. Let me say that again. Because we have a random variable, we are able to numeralize the events or the results from an experiment. This is a very, very important, how do I say that, milestone in the history of the development of probability and statistics. Originally, we used like a capital letters A, B, C, D to denote events, and the events are better expressed in words. Like you flip a coin, you get a head or you get a tail, right? But since we have the random variable, we are able to numeralize the results. Then because we are able to numeralize the results, we could use the real analysis in mathematics, like other branches of mathematics, to study probability and statistics. So as I mentioned, as I said, bring in random variables in probability and statistics is a milestone in the development of the branch here. By the way, we're supposed to use capital letter X, Y, Z to represent the random variables. The lowercase x or y, z, they are the values of the variable could assume. So this is the difference. I think I'd better give you an example to make it clear that what is a random variable. For example, a very simple example. Let's think about flipping a coin. We know the sample space contains two outcomes. You either get a head or you get a tail, right? We can say the two outcomes are not numerical. From surface, you don't see they related to any numbers, right? However, if I bring in a random variable x and let x represent the number of head in the result. If I bring in the random variable x, let x be the number of getting head in the result in one flip, then we could numeralize the results of the experiment. The outcome getting head. So if you flip a coin, you get a head. Then what's the number of getting head in that trial? 1, right? So the event H would be the same with x equals 1. Do you see what I'm saying here? X equals 1. If the random variable x assume value 1, that means the outcome that getting a head occurs. So what if we flip a coin and we get a tail? If we get a tail means we have no head, right? So the number of head in the result in the trial would be 0. So if random variable x assume value 0, that means when we flip a coin, we get a tail. Do you see what happened here? Once we bring in a random variable, properly assign the meaning for the random variable, then we could numeralize the results from the experiment. In this simple example, the random variable x equals 1 represents the outcome you getting ahead. Random variable x equals 0 represents the outcome that you get a tail. So we are able to construct the probability distribution for the random variable x here. Probability distribution of a random variable x, sometimes actually x here, random variable x here is the population. we could construct the probability distribution for the random variable x. Probability distribution of a random variable x is a two-column table as well. Column 1, we list all the possible values for the random variable x. In this case, x either assume 1 or assume 0, right? You don't have any other values, do you? So either 0 or 1. 0 and 1 are all the possible values for the random variable x. And in the second column, we're going to have the corresponding probability for the random variable x assume each value. So here we're going to have the probability of x equals 0. And here we're going to have the probability that x equals 1. Okay, so what is the probability of x equals 0? Let me explain here. The probability of x equals 0, x equals 0 represents the result, the outcome that you get a tail, right? Equals the probability that you get a tail, which is a half or 0.5. Is that understandable? The probability that x equals, okay, so I'm gonna unbutton that. Probability that x equals 1. X equals 1 represents the outcome getting ahead. So it's the same with the probability of h getting ahead, and that is a half as well, 0.5. So this two-column table is called the probability distribution for the random variable of x. This two-column table is the probability distribution of random variable x. Okay, column 1, we have all the possible values for random variable x. Column 2, we have the probability for x assume each value. Look at the second column. In this probability distribution, we have two numbers in the second column, 0.5, 0.5. They add up to 1, right? Exactly. So that is one property about the probability distribution. The second column, in a probability distribution, all the probabilities in the second column must add up to 1. Must add up to 1. So that is the second requirement. Second requirement for a table to be a probability distribution. The probabilities in the second column of the probability distribution have to add up to 1. Where x assumes all possible values, the sum of all probabilities must be 1. But the sums such as 0.999 or 1.001 are acceptable because they result from rounding errors. Number 3, in the second column of a probability distribution, those numbers are probabilities, right? So those numbers must be between 0 and 1. For every individual value of the random variable x, that is, each probability value must be between 0 and 1, inclusive. In previous videos, we talked about a general definition for probability. Probability is a value, is a number between 0 and 1. Inclusive means it could be 1, could be 0. If it's 1, then the event is certain to occur. If it's 0, then the event is not possible to occur. That number, that value measures or describes the likelihood of an event occurring. So those three requirements must be met in order for a two-column table to be a probability distribution. I think we have a related problem in the package. We'll look at it later. Let's look at the example in the notes. Consider the number of girls in 2 births. Find the probability distribution and graph the probability histogram. So let's make the table first and then talk about the histogram. Let's see what is the random variable x here. Very natural. You would let random variable x represent the number of girls in 2 births because we are constructing the probability distribution for that variable, right? Of course, x represents the number of girls in 2 births. It is a variable. It is a random variable. It's not a constant because some family with 2 births could have no girls at all. Both of the children are boys. Some families with 2 births could have 1 girl only. Maybe the older one is a girl or the younger one is the girl, right? And then some households, maybe both of the 2 children are girls. So the number is a variable. So we're going to use the random variable x to represent the number of girls in 2 births. We are constructing the probability distribution. In column 1, we need to find all the possible values for x. All the possible values for x. It could be 0, as I mentioned. Could be 1, could be 2. Do we have any other options for the values of x? No. You wouldn't have 3 girls in 2 births, right? That's not possible. So all the possible values for x are 0, 1, 2. So that's the first column. And now let's find the probability for each value that the x assume. I'm gonna erase that. Let me first one, p of x equals 0. Okay, how do we find the probability of x equals 0? Means you randomly select a household with 2 births and no girl in the 2 births. Do you guys remember we have learned the 3 definitions for probabilities? Before we compute for probability, we would have to identify what type of probability we are talking about, right? So we need to find the experiment in this example. What is the experiment? What is the sample space? Okay, the experiment, you can see the experiment here as you go somewhere and you randomly select a household with 2 births and you record the number of, well, hold on. So you record the gender. You record the gender of the 2 births. Okay, so what do you think? 2 births. How about this? When you record the gender for the 2 births, you wanna firstly decide how do you record it, right? So this is how do we record it. I'm gonna put the gender of the older child here and put the gender of the younger child here. Okay, so you go randomly select a household with 2 births and you write down the gender for the older child and the gender for the younger child. So the older child could be boy, could be girl, right? So you have 2 possibilities. And the younger child also could be girl or boy. You have 2 possibilities, right? So you have 4 options in total. That is the fundamental counting principle. Yeah, I should have, let me explain what is fundamental counting principle. I want you to please relate this simple example whenever you think about fundamental counting principle. The example here is, if you have 2 ways to go from A to B, and 3 ways go from B to C, then how many different ways do you have, or different routes do you have from A to C? This problem or the process has 2 steps, right? Step 1, you go from A to B. Step 2, you go from B to C. Then how many different routes do you have go from A to C passing B? You would have to consider, you would have to complete part A and then complete part 2 to complete the whole task, right? How many options go from A to B? 2. How many options from B to C? 3. So how many options do you have from A to C passing B? Please don't tell me 5. You have 6. 2 times 3 equals 6. You're going to apply the multiplication rule here. 2 times 3 equals 6. You have 6 options, 6 different routes from A to C passing B. I can show you. From A to B, you can choose this route, right? So 1, 2, 3. From A to B, you can choose this route. Another 1, 2, 3. 3 plus 3 is 6. 2 times 3 is 6. That is a fundamental counting principle. Fundamental counting principle tells us if you have a task, the task has 2 parts. Well, you could have more parts, would be the same idea. Here, I want you just to relate this example. The task has 2 parts. Part 1, you have n different ways to complete part 1. You have m different ways to complete part 2. Then you would have n times m. You are multiplying different ways to complete the whole task. That is a fundamental counting principle. Now let's go back here. So you are recording the gender for the 2 children in the household, right? For the first children, you have 2 possibilities. Second child, you have 2 possibilities. So by the fundamental counting principle, you have 4 options. The 4 options, they are, actually we are finding the sample space. Boy, 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 girl, girl, boy, girl, girl. You only have those 4 outcomes. Do you have other outcomes? I don't think so. So you only have those 4, 1, 2, 3, 4 outcomes. And are they equally likely? Recording, rolling 2 dice together. That example. This one actually is similar, very similar. They are equally likely by the symmetry. If we assume getting a girl and getting a boy are equally likely, we don't talk about like a genetic or other complicated case. We assume getting a girl and getting a boy are equally likely. Then those 4 outcomes are equally likely. So we are talking about a classical model, right? Classical model. Then what is the probability of x equals 0? Probability of x equals 0 means no girl. No girl means 2 boys, right? So BB is a classical model, so the formula is k over n. What's the value of n? 4. That's the total number of outcomes in the sample space. What's the value for k? The numerator. K is the number of outcomes in the sample space favor the result. 1. So that is 1 over 4, which is 0.25. Is that understandable? Okay, so let's see how do we find the probability of, let me move this. You know, one benefit of doing the video is I don't have to rush. We don't have a time frame. I have to finish like in 1 hour and 19 minutes. I can do more actually. Okay, so let's see the probability of x equals 1. How do you understand this numeralized result? What does x equals 1 represent? It represents the 2 children only has, among the 2 children, there is 1 girl. The other one is a boy, right? So 1 girl, 1 boy, 1 girl, 1 boy. Those 2 outcomes favor 1 girl only, right? So by the definition k over n, the theoretical probability, the denominator is 4. The total number of outcomes in the sample space. Numerator is the total number of outcomes in the sample space favor the result. Only has 1 girl. The other is boy. 1 girl, 1 boy. So we have 2 of them here favor the result. So 2 over 4, which is half. 0.5 here. You see that? Okay, the last one. X equals, let me write it here. P of x equals 2. What does that mean? X equals 2. X equals 2 represents both of the two children are girls. So P of GG, 2 girls. By the theoretical probability, it is K over N. The denominator N is 4, total number of outcomes in the sample space. Numerator is the number of outcomes in the sample space favor the result. Both of the children are girls, right? So that is 1. 1 over 4, a quarter, 0.25. So that's how do we have the probability distribution table for the random variable x. Let's double check. In column 2, all the 3 probabilities are between 0 and 1, and they do add up to 1. The sum of the 3 probabilities is 1. Okay? So one more thing about the probability distribution is the expected value of x. We are going to talk about that concept in the next video. I'll see you soon in the next video.